Thank you, Professor Beklemishev, for this introduction. Yeah, you may be surprised to see no concept in the title, but it's supposed to, yeah, you will see them later on. But my idea was to use the observation that this faculty can be rather called not the faculty of computer science, but of machine learning. Every student is obsessed with machine learning, so I wanted this title to be sort of teaser to attract them, but I don't see them. Maybe the second part of the title scared them away. So, but anyway, let's start. First, I will speak on the motivation, then, and present some history of some short history of dualization, introduce you to this problem, and then we go to the lattice of closed sets, also called concept lattice, and we show that a natural machine learning problem can be reduced to is shown to be equivalent to a problem on dualizing on lattices of closed sets. And then we consider this problem, I mean, dualizing on lattices of closed sets given by irreducible elements, and show that, unfortunately, in this case, positive results known about dualization algorithms don't hold there because of possible exponential blow-up when you come from data to lattices. And then we have some discussion of the results. So let's start with this picture. Which gives you a sort of iconic representation of dualization problem. But to mention a machine learning setting, we can say that it's like in vector spaces where one of the popular machine learning approaches called support vector machines builds a hyperplane to separate positive and negative examples of some target attribute. When you have a discrete learning problem, where your data is given by vectors or tuples of discrete attributes, in the simplest case, binary attributes. A monotone Boolean function is like a hyperplane, which you can separate your positive examples from negative examples. Or it can be viewed also it can work in a bit different way, where not just the anti-chain, which defines a monotone Boolean function, is separating entity, but the order ideals are separating positive from negative examples. In any way, monotone Boolean functions are very good models for classifiers. And consider the following natural problem of learning a monotone Boolean function from membership queries. Given an oracle, deciding whether a function is true on a vector v for a monotone Boolean function f and a given vector of values v, compute the boundary given by minimal true values and maximal false values. Like they are shown here as set A of minimal true values and set B of maximal false values.
So we just need to reconstruct the function completely.
Yeah, actually, yeah. With this two anti-chains, you have this function and even more than that. Because what is above is true, and what is below is false. Bloch and Ibaraki showed more than 20 years ago that this problem and many other similar problems are equivalent to the problem of dualizing a monotone Boolean function, which is not surprising, having this intuition of the Boolean function. So the major problem is, can these and similar problems be solved efficiently? I put it in quotation marks because the definition of efficiency should be considered in more detail, because the output can be actually exponential in the input. So efficiently in this case can be something like polynomial delay or similar notions. So let's start from first definitions. Sorry for those who know already very well what is dualizing it, but I have to repeat it to make the talk self-contained. So dualizing a Boolean function is a well-known problem. If it's an arbitrary Boolean function, you just take negation of variables and negation of the function, or you just interchange conjunctions and disjunctions and zeros and ones, and you get to this your dual function. But dualizing is quite tricky when formulas take a special form, like prime conjunctive normal forms. And prime meaning that you cannot delete a literal from a clause, from a disjunction, which makes the CNF. So here we have a small example for this CNF. Its dual will be this, and it has this prime CNF. Again. And in general, constructing a dual CNF by applying Boolean, just simple Boolean laws of distributivity in this case, will not help, meaning that it will not give you an efficient procedure. Let's recall another important fact about monotone Boolean functions, that they have unique prime conjunctive normal forms with only positive literals. So you can think of a monotone Boolean function as a monotone conjunctive normal form. And then dualization problem can be stated in the following form. Given a prime CNF of a monotone Boolean function, so positive CNF, construct the prime CNF of its dual. This dualization problem is important not only by itself, but by many equivalent problems that are often encountered in computer science. Like computing transversal hypergraph to a hypergraph. Having a hypergraph which you can represent by a binary matrix, for example, where rows stay for vertices and hyperedges stay, and columns stay for hyperedges. Find a hypergraph with the same set of vertices and hyperedges being minimal transversals. So subsets of the set of vertices which hit every hyperedge. And computing all these minimal transversals, is, by doing this computing transversal hypergraph, is polynomial equivalent to a dualization problem. Sorry, I forgot to cite a famous survey of Thomas Eiter and Gottlob of 90s, where they consider this particular problem in details.
Just a stupid question. So how the size can increase? So we have a prime CNF and want to find the duals. Can the dual will be, for example, exponentially large than the original?
During your expansion, it can become exponentially larger, yeah.
So that can be a short prime CNF with a very long.
Yeah. A famous problem of computing on minimal set coverings, which are actually also transversal. This equivalence is very simple to show. And maximal independent sets of a hypergraph, so the sets of vertices which are not connected by any hyper edge, is a complement to the covering problem. So computing on maximal independent set on the complement of the hypergraph is same as computing on minimal set coverings of initial hypergraph. And then finally, not finally, the last in this list, which can be extended to dozens of similar problems, is computing minimal true vectors of a monotone function given maximal false vectors. So back to this picture, given one of the boundaries, compute the other boundary. So maximal zeros from minimal ones or vice versa. Dualization is polynomial time equivalent to the following decision problem. By that, so far we considered problems where we had to compute something to output. And often in complexity theory, one reduces a problem to a decision problem. In this case, its natural form sounds like that. Given a prime CNF of a monotone Boolean function, of monotone Boolean functions f and g, decide whether f and g are dual Boolean functions. And a famous result by Fredman and Hachiyan published in 1996 is based on an algorithm which runs in quasi-polynomial time in the size of the input. In contrast to previously known algorithms which were purely exponential. Having this complexity, we can say that this decision problem is hardly NP hard, because no NP hard problem is known to have quasi-polynomial solution. Yeah.
So dualization could be exponential time because the output might be exponentially big, right? But you're saying this dual recognition problem, or what is that called? Do you think quasi-polynomial time? So, I'm sorry, forming the dual, I said the wrong word, is exponential time because the output may need to be exponentially big.
Yeah, I mean, in the size of the input, or of this input.
But dualization is almost conforming, right?
So the size of the input is, so to say, exponential.
No, so the problem of checking is difficult when f and both formulas are short.
That's
Still it's not clear whether they are dual or not.
So when you say there's polynomial time equivalent, you get the polynomial time reduction is equal more than something different.
Sorry?
What is the exact meaning of this polynomial time equivalence?
I mean, it's carp reduction in both ways.
Between decision problems.
Oh, yeah, sorry. A reduction, yeah, yeah, sorry. It's not carp, it's just polynomial reduction.
So this is decision problem, that's clear. But how do you say that, what is the...
No, but the point is, if the formula dual is exponential time because the output needs to be exponentially big.
Yeah.
Right? And this you're just proves quasi-polynomial time.
Yeah, but it's formally, there is no contradiction with output is good. But for the dualization, for this checking problem, the output is part of the input. So G is the output.
Jeez.
Yes, I understand. I don't understand how that.
No, just we are...
Algorithm. The previous algorithm is exponential time. This is polynomial time.
Yeah. We need to understand what this polynomial time equivalent means.
Yeah.
Or just decide that we don't understand. Because, for example, there is, you say, the dual decision problem has a Cauchy-Yang algorithm. That implies something for dualization. If you say there are polynomial time equivalent, and there is a simple algorithm for dual decision problem, what is the implication for dualization?
Output polynomial.
Right, so output polynomial makes sense. Okay, maybe that's what you mean then. Okay.
Oops, sorry.
But how the Cauchy-Yang, you have some slide. Maybe you can say how.
Yeah, it's just few hints how they do it. The main idea is based on the observation that for CNFs phi and psi representing function and its dual, one has this fact, and this implies that phi or psi contains a short conjunction, which size is smaller than that. Where C is a clause of an arbitrary clause of phi or psi. And having this fact for any pair of phi and psi, one shows that there exists a frequent variable x sub y with this frequency sufficient enough, which is larger than that. And then one decomposes these functions in a way that the decomposition are smaller than the original phi and psi, and iterates. And this bounds gives the possibility to show that the number of iterations is not that large. And finally, they get this upper bound.
So, can you comment what is frequency, why it's large? So you say that there is a variable which is contained in many.
Yeah, frequency. There is a short conjunction, which is,
short conjunction, otherwise we cannot cover the space.
yeah, and then with this fact, it says that there exists a frequent variable with a frequency such that the frequency is the number of clauses where this variable occurs. With the relative number, over the size of the fab.
Or inside.
Yeah.
The point is that there's a short clause, C, and any little in C appears in every clause of the dual function. And so, because there's only a few variables in that short clause,
One of them should be, and if we make a decomposition of this, would decrease that the other.
Yeah, and that's, you need 2 lectures to tell this in detail, but it's just a part of my survey. And this paper calls the wave of extensions and generalizations. And for example, Bassioni in his papers, several papers showed how these results can be generalized to different ordered sets. For example, product of partially ordered sets where each partial ordered set has a special property. For example, is a joint semi-lattice of bounded width forest offset, or a set of lattice of intervals.
So now
And
the function is a function of which arguments? We have Fourier functions, and now
they are generalized to posets. So function is a Boolean function, but it's defined on a poset and on an ordered set.
Argument, it has several arguments, and each argument belongs to its own poset.
Yeah.
Yeah, and it's monotone with respect to this.
Yeah, but what is important here is that, and what is important will be important in later sections, that ordered sets are given explicitly. Lattices are given explicitly as ordered sets.
So their sizes are parameters of the
Yeah.
polynomial.
Yeah, exactly. Well, that's the point. Their sizes are parameters. And further on, we'll speak about other representation of lattices which represent them implicitly. And that will make a difference. But here, sizes are really parameters of the input. So in a sense, lattices are given explicitly. Yeah. So far with this short survey, and I will come, unfortunately, I have first to give another motivation, which comes from a learning model, so-called GSM method of hypothesis generation, formulated by Victor Ruffin in 80s and 90s, which is based on the idea of John Stuart Mill and his famous methods of inductive reasoning, based on the idea that similarity of effects is due to similarity of causes. These ideas of Mill were transformed by Finn in a sort of learning model, where you have positive examples of a target attribute, negative examples of the target attribute, and undetermined examples, where you don't know Let us consider this toy example. So our target attribute is fruit, and we have positive examples 1 to 4 and negative examples 5 to 7.
What is M and G? There are something in the previous slide.
Oops, yeah, sorry. G is for Gegenstände, objects. Sorry, I use this so-called Darmstadt notation. I just came to this part, yeah, not explaining what is below. G stay for sets of objects. Here they
G is some set just.
yeah, G and M are sets, and they are interpreted as sets of objects and sets of attributes. Sorry, this is from German Gegenstand, object, and M Merkmal, attribute. Yeah, here they are many valued attributes, but we easily transform them to binary. I will show you. But first, the idea that you should look for explanation what is a fruit in or not a fruit, why an object is a fruit or not a fruit, in observing similarities between fruits and not fruits.
Also, it's not set difference. It's just.
Yeah, sorry. It's just sorry. It was like.
So the G is just this.
Yeah, no set difference. Yeah, it's just. G refers to rows and M refers to columns. So you should, based on this idea of John Stuart Mill, you should look for explanation of why something a fruit, observing the fruits and finding similarities. For example, here, what is yellow and not firm and round will give you a hypothesis of why something is you can call something a fruit, because this similarity, similarity of two fruits doesn't have any counterexamples here in not fruits. If something is yellow or not firm and round, then it should be a fruit in our small world. Same with white here. If something is white, then it's plausibly not a fruit. So similarity here is considered as common as intersection of attributes. But you can do it in different ways. But you, for example, you can binarize the attributes. Look at this table below. You introduce binary attributes instead of color, so white, yellow, green, and blue, firm, not firm, smooth, not smooth, round, not round. This could be done more accurately, like introducing oval, but we did it quite in a rough way. So, we observed this similarity of positive examples, yellow, not firm, round. And this set of attributes is not contained in any description of a negative example. So it can be considered a positive hypothesis according to Mill and Fien. Similar to a negative hypothesis, like white, similarity of egg and tennis ball is a good negative hypothesis because it doesn't include in any description of a positive example.
So if you consider each line as a vector, so then we have some positive string and negative strings, and we want to find a code which doesn't contain any negative point, it's positive hypothesis. Monotone Boolean, monotone.
We are not yet, but let's consider hypothesis. I'm sorry for that. A positive hypothesis in this binary representation is an intersection of any subset of positive examples which is not contained in any negative example, in the description of a negative example. Like yellow or not firm around isn't contained here. But if we take the intersection of all of them, it's just not firm, and it has a counterexample tennis ball, and that not firm is not a good hypothesis. It is falsified. So what we need here is that we look for hypothesis. What's that? We look for hypotheses as intersections of rows in this table. But intersections can be represented as closed sets of attributes where closure can be defined in a very natural way. And to define it, we have to go back to the definition of lattices of closed sets. So I introduce you shortly to this model of which they call formal concept analysis. What we have in the beginning, we have a binary relation which they call a formal context. The G and M are sets, and I is a binary relation on them. So you can see it as a binary table. These are objects given by rows, and these are attributes given by columns. And then we define two. Oh, sorry, I have to switch it off. Two operators, which traditionally denoted by prime, give a Galois connection between the power sets of set of objects and sets of attributes. A prime takes a set of objects A, subset of objects A, to the set of attributes common to these objects. And B prime takes a subset of attributes B to the set of objects that share these attributes. So, for example, 1, 2 prime will be just A, and AB prime will be empty. AB prime will be empty because no object has these two attributes together. A formal concept is a pair AB such that a set of objects A have all attributes from B, and all attributes from B are shared by all objects from A. In a cross table, staying for this relation, or how they call it, context, concept corresponds to a maximal subtable filled with crosses. You cannot extend it without adding a column or a row with an empty entry. So this stay for a formal concept 3, 4, BC. This pair has a nice interpretation in logics and even philosophy. You can call this a concept because A can be interpreted as extension of a concept. So all objects subsumed by this concept, and B is the meaning or intention of the concept. In our case, it's just a set of attributes. The concepts are partially ordered, and this order makes a lattice. This was known to Birkhoff. You can find it under the guise of polars in the book on lattice theory. Polars is the Birkhoff's name for these two mappings, primes, which actually make a Galois connection between the power sets of G and M.
So one can say that we are all for maximum B clicks.
Yeah, it's cryptomorphic, to biclicks. If you take objects and attributes as disjoint sets of vertices, then concepts will correspond to biclicks in a bipartite graph.
Which are maximal. Concepts should be maximal. Maximal biclicks,
Yeah, you cannot extend them. So what does it mean, a lattice? Any two concepts have supremum, in this case it's this, and infimum, with respect to the order on concepts. This was known to Birkhoff. You can find this in his book on lattices. But more interesting fact, already known to Barbu and Monjardin, infinite case, and then proven in more rigorous terms by Wille, decade later, for general case, that every finite lattice can be represented as a concept lattice. It was shown by Barbu and Monjardin. So for any finite lattice, you can propose a binary relation such that it will give rise to the concept lattice, which is isomorphic to your original lattice. For example, how you do it, you take irreducible elements of the lattice. So this element is infimum irreducible. It cannot be represented as infimum of any elements above it. And you take it as an object, and every supremum irreducible, like this one. Sorry, other way around. Infimum irreducible are taken as attributes, and supremum irreducible, like this one, which cannot be represented as supremum of anything below it, are taken as objects. And here the relation is just the order in your lattice. And when you make this context from your original lattice, you get a concept lattice which will be isomorphic to it.
Can you comment, so the supremum and infimum in terms of this bipartite graph is what? So imagine we have two big clicks.
Yeah.
So what is supremum and infimum?
It's very simple on one side and a bit tricky on the other side. So if you have two biclicks, you intersect on the one side, but on the other side you take double prime of the union.
But it should be symmetric somehow. If it's lattice is symmetric with respect to size.
Yes.
Somehow the infimum can be
look at this. Let's look at this. These are your biclicks, yeah? You intersect them, D and this and this. You get this part is just intersection on 1, 4 and 2, 3, 4. But this is not just the union of C and D. it's double prime, you apply prime twice, to the union of C and D. So that's how you get infimum. And supremum is dual. You just unite your intents. Oh, sorry, you intersect your intents, like BCD and AC, and you get C. But you take the double prime of the union of 2 and 4, and you get not just 2 and 4, but 2, 3, 4.
But the ordering, how is defined? You said that.
The order is very simple. It's just a containment of or reverse containment. So like
on one side should be contained, or what you
like archetypic example, like natural classification. Take mammalia is more general, or vertebrata is more general than mammalia. So all mammalia are vertebrata, but mammalia share more common attributes.
So in one side,
What is also important here that, what is important here that the double prime operator is closure, is idempotent, monotone, and extensive. So this meaning that A is a subset of A double prime. Idempotent meaning that A 4 primes is equal double prime. And this means that, yeah, it's clear. Yeah. Is it not clear now? So to represent a lattice as a concept lattice, you take it join and meet. Oh, I'm sorry, I will use this terminology. Supremum and infimum irreducible elements and order relation on them. And when you compute the concept lattice, it will be isomorphic to the original one. So that shows you that your a lattice can be compressed sometimes, unfortunately. In what sense? It can be represented by its irreducibles. It's sometimes very compact, much more compact than the lattice. The simplest case is the Boolean one. The irreducibles are atoms and coatoms. You write your objects will be atoms, and the coatoms will be attributes. And the corresponding relation for the Boolean lattice will be complement to diagonal. So the diagonal will be empty, and the rest will be filled with crosses. So in doing this, you compress your lattice exponentially. The Boolean lattice of size 2n you represent with the context n times n. But there can be compressions in other cases. Say for distributive case, there can be huge compressions as well. But of course, there can be cases when the number of irreducibles is compared to the number of to the size of your lattice. Like you take say the lattice which is like diamond, Yeah. And it with n elements here, and then its context will be just the diagonal with n elements here and n elements here. So you, in a sense, you cannot compress it, represent it shortly, in a shorter way. Yeah. Here's a reminder what Sharp-P complete, and we have to proceed with computation problems. So, given a context, concept lattice can be exponential in it, and determining the size of a lattice given its context is the Sharp-P complete problem. So these are bad news, not quite news, but good about that is that you can compute the concept lattice with polynomial delay. So you spend polynomial time between outputting next concept or terminating. And they have this polynomial delay, and there are some champions. This is the champion, which is totally impractical because it uses a suffix tree which grows it. It requires exponential memory, actually. Doesn't have any decent implementation. What is good about these concept lattices and closure operators is that they propose also a nice notion of dependency. We'll use it later on. It's called implication. Implication between two sets of attributes A and B holds if all objects having attributes from A also have all attributes from the set B. In terms of primes, it's written like A prime subset of B prime. Our implications can be seen in the lattice diagram. I will talk on that. And they satisfy Armstrong rules, which relate them obviously to functional dependency in relational databases and to Horn theories. And an implication cover is a subset of implications such that other implications can be inferred from them by means of Armstrong rules. And the base is a minimal by inclusion implication cover. That's what we need so far. And then we come back to our hypothesis. And using this definition of the hypothesis, which is just intersection of rows in our data table, of positive rows, which is not contained in any negative row. We can say that hypothesis is a closed set of attributes, because every intersection is a closed set of attributes, closed with respect to prime operators, prime operator. For example, you see, white is intersection of 6 and 7, and here, white is intersection of 6 and 7, and if you take white prime, you go to 6, 7, and 6, 7 prime gives you white. So it is closed in terms of I can put it white minus minus is white, where minus here superscript denotes prime operator in negative context. Same with yellow. are yellow or not firm and round. If we take its prime in the positive context, we come to objects 1, 2. And if we take prime in the positive context of 1, 2, we get back to so yellow, not firm, round is a closed set of attributes with respect to the prime operators in the positive context. So it makes intent of a formal concept in the concept lattice of this context, in this relation. And we need also to satisfy this condition that hypothesis doesn't have any counterexample. So this set of attributes, to be a positive hypothesis, it should be closed, which is equivalent to being an intersection of rows. And the second condition, it shouldn't be contained in any negative row, which holds here. But doesn't hold, for example, for this subset of attributes, which is not a hypothesis. So, all these concepts of this positive context correspond to hypothesis, except for these two. This not firm is contained in 7, and this one is also contained in the description of a negative example. So these are not hypotheses. How we use hypotheses? We use them as classifiers. We have learned them, and then we use them as classifiers to predict the target value of some new arriving objects, like this Mango. With this description, it's strangely, it's green, not firm, smooth, and not round. And we would like to know whether it's fruit or not. In this case, we would take the hypothesis based on smoothness. Yeah, and it's here, not firm, smooth, and say that mango is plausibly a fruit because it contains positive hypothesis but doesn't contain any negative hypothesis. It is not white, and then the second negative hypothesis firm and smooth and not round, which is not the subset of attributes from Mango. So we use them in this way, and of course, to do classification, we need only minimal hypothesis. Minimal on the intent side. Minimal hypotheses make an anti-chain in the concept lattice. So these three hypotheses are minimal. And they define a monotone Boolean function on this lattice. Everything below is a positive hypothesis. Everything above is not a hypothesis. It's falsified. So minimal hypotheses are then maximal zeros of a monotone Boolean function given on this concept lattice. And they are determined by the positive context and negative examples. So negative examples determine minimal ones of this monotone Boolean function. So we, having a lattice described implicitly by its context, and having minimal ones given by negative examples, to compute a minimal hypothesis, we actually need to compute largest zeros of this monotone function. Some of the problem of enumerating them is stated as a learning context. So this context with positive and negative examples. And first we state the problem, generate all hypotheses. Interestingly, it's quite trivially, it can be shown that it's can be done with polynomial delay. You actually take some of well-known algorithms for computing lattices and add a another backtrack condition. If you reach the boundary, you backtrack. And you easily get a polynomial delay algorithm for computing all hypotheses. But a long-staying problem was that of enumerating just this antichain of minimal hypothesis. And with Mikhail Babin, we showed that this cannot be solved in output polynomial time unless p equals in p, unfortunately. So once again, all hypotheses can be generated with polynomial delay, although the problem of computing the number is sharply complete. But this antichain cannot be generated with polynomial delay unless p equals in p, general case. And I also showed you how it's related to dualizing a monotone function on a lattice given implicitly by its context and minimal ones given by negative examples. To prove that it cannot be generated with polynomial delay unless p equals in p, we use the following trick, which is used in similar proofs. Because it's not a decision problem to output all minimal hypotheses. But you show that it's not solvable, it's not tractable by this trick of additional entity. In this problem, you have your input data and some subset of minimal hypotheses. And your question is whether there is another minimal hypothesis which is not contained in this set B. It's obviously a decision problem. And if you show that it is NP complete, then you cannot have a polynomial delay algorithm for generating the whole set of minimal hypotheses, because it would...
Why? It generates in different order. What is the relation?
What do you mean by order?
We have some, imagine we have an algorithm which generates some set with polynomial delay. But now we have some. So how many minimal how large is the set?
It's the input, so it doesn't matter in a sense.
So this polynomial delay, does it mean that the delays between outputting successive
Yeah, or terminating,
they're polynomial in the size of the
Yeah. Several notions. This just sorry. Go back. Yeah, it was introduced by Johnson and I think Yanakakis, and there are milder versions of that. Say cumulative polynomial delay when it's also a function of your output. So far. Yeah, and total if it's polynomial in the size of the input and output, final output. But here we
and there is a fixed polynomial which sort of finds all these delays.
yeah. That's for our concepts. It's like G squared M. For many algorithms, we know.
Oh, and now you say that this problem of minimal hypothesis.
Addition. This is a. Sorry. No, it's next. Sorry.
Yeah, so this problem is NP hard even if we allow, if the time is bounded by the size of the subset.
Yeah.
It would be theoretically very large.
Yeah.
Even in this setting, it's still NP hard.
Yeah.
Yeah, then yeah.
This original problem to
You-
generate all possible hypotheses. What kind of tasks is it useful for? I mean, I suppose that this is a standard for the equation. Why not?
All hypotheses. Yeah. Yeah. That's. Yeah.
Do we really need to know all of them?
Yes. Yeah. So I don't sell it as an important problem. Unfortunately, the important problem would be to generate the minimal ones, but you cannot do it quickly. Yeah. All of them, yeah, you definitely, they are redundant. Yeah, you don't need this, and this. If you classify with this, you can classify with something smaller, with some minimal hypothesis. So you really don't need all of them. You need this anti-chain.
But just more general question. So this whole thing can be probably considered with different angles. So you can think it's just a kind of philosophical question, how we create notions and how they change it with your objects and what is the structure of notions. So this is one philosophical idea. Also, one can think as a practical learning problem which can be applied for something. Or just as a nice combinatorial question, which it can be used as an example for reductions or for. So, how this viewpoints what is main somehow viewpoint or when we look at this, what is our
So there's many-fold. It's really used in practice. This learning model is used in practice.
So if we use them in practice, what is the scheme? So we start with the table.
Yes, we start with with our training data,
Yeah.
positive and negative examples. we generate hypotheses, and then we apply them to new examples to classify them.
And then, for example, if we just then some natural question arises. Imagine we have this new example, and we classify it, and then we do a bigger table.
Yeah.
And so, for this bigger table, what happens with the notions, hypothesis? So,
Yeah, unfortunately, it's not stable. So you cannot guarantee that a next counterexample would.
if it's not a counterexample, if we successfully predict something, and then we just enrich our table with something completely predictable by the previous hypothesis, do they stay still? The same hypothesis remain valid, or they become non-minimal, or
they can become non-minimal.
We don't see a counterexample. If we see a counterexample, I understand that things change. But if we don't see a counterexample, can we say that hypotheses are more or less the same?
If we don't get a counterexample, then hypothesis will stay hypothesis, but they can become not minimal. Minimal at one step can be non-minimal at the next step. Yeah. Of course, it's sort of plausible reasoning, which you can apply without any statistical and before any statistical reasoning. Because you can do it with quite small sets of data where you cannot use any statistical reasoning reasonably.
So, for example, imagine we have, I don't know, 1,000 objects, like 1,000 students, and 10 or 20 attributes, like 20 exams or something like this.
Yeah.
So, what is the feeling? So, if we start all this algorithm, what do we have? We have billions of hypotheses, and we are lost, or we have 3 or 5, or just what kind of practical situation you expect to clear?
Yeah, you're right. We have often exponential explosion, but then we have to filter them according to some quality indices. We have several. Actually, data mining is about this filtering according to some criteria. So they can be, even minimal hypotheses can be considered as raw
But the task of
raw
generating
dependencies.
the minimal hypothesis isn't feasible, even if you want to generate them, and there are probably a lot of them.
You know,
What is the stage of it?
recall this. Have you been at the talk by Moshe Vazirani? I think it was. He was talking on Yandex that he said that when he was young, then saying that the problem is in P complete meant that you cannot approach it closer than 10 feet. But now, and he showed the slide on SAT solvers. We have this progress with SAT solvers showing that every year the practical time used to solve SAT problem increases twice, so almost exponential growth of the speed of SAT solvers. So in practice, we deal intractable problems.
No, but just the number of, if we have thousands and hundreds, 1,000 objects, 100 attributes, so the number of minimal hypotheses in practical, of course, probably can be big theoretically, but what if you take some real data of this magnitude, you will encounter just thousands of them, or millions of them, or exponentially unfeasible number of them.
Yeah.
Actually, simply asking for one concrete application, so to say, describe what was the database to which you applied.
Yeah, that's unexpected question from this audience. Yeah, I have nice slides about this, but not here. An application on predicting toxicity of biological compounds. So instead of this toy example, we had a target attribute staying for toxicity of compounds. Here, say hundreds of toxic compounds, about 100 of non-toxic. And here, the attributes stay for molecular fragments of compounds. And so we...
20 of them, or what number? Order of magnitude.
Also 100.
Yeah, so
like
you
100.
have 100, 200 in this direction, 100 in this direction, and then you apply these algorithms, and how many minimal hypotheses do you get, just to get some feeling on it? It's like
in that case, it was not that big. It was like 100 again.
Oh,
It
so
was
something which can
it was a very sparse matrix because molecular fragments. So every molecule was described by quite few fragments. So the matrix was quite sparse, and we produced classifications which were then validated and were quite good. Because it was, in that case, it was a competition. The organizers of the competition knew in advance the correct classifications of this kind of new objects. So we did quite a lot of correct predictions, but with the classification scheme we used, we had many cases where we didn't give a definite answer. When positive and negative hypotheses meet, we just said we don't say anything. We reject it, to abstain from classification. But actually here you can have plenty of solutions based on weighting the classifiers, weighting this minimal hypothesis, saying that this is better because this fragment is more important or something like that.
In this example, the number of minimal hypotheses was quite visible, and the algorithm was practically used.
Yeah.
Even if it's NP complete, as you have proven, it's not a practical problem.
Yeah.
Of such size of.
Yeah, but so even at that time it took just minutes to compute everything. I'm sorry, we are running off time, and I have 5 minutes. Yeah, that's a nice trick, which I should say is a general trick. It's not our invention. I mean, in general, how you prove that something cannot be produced in total polynomial time. Construct this additional entity problem, yeah? Where entity can be anything. In our case, it's minimal hypothesis. And the question will be, is there another one? And then we reduce set problem to it, taking an arbitrary conjunction. We construct a relation. These are objects, these are clauses, and this is positive context, this is negative context. Yeah, we don't have time to do this. That's an example. So that's an ordinary reduction of satisfiability problem to this one. And just a few words on another setting. Actually, I described it before by considering the example with the fruits. Yeah? That you can represent the monotone Boolean dualization on a lattice as you can show that it is equivalent to the problem of computing minimal positive hypothesis from positive context and negative examples. And then it shows you that if a lattice is given as a concept lattice, so by its irreducible elements, then dualization cannot be solved in output polynomial time unless p equals in p. And this makes a big contrast to the results of Fredman and Hachiyan and subsequent results which adapted the techniques of Fredman and Hachiyan. And it's because our lattice is not given implicitly. Our lattice can be given, say, by matrix n times n, whereas it is actually exponential in n. And that's why we have hidden exponential blow-up, which doesn't allow us to apply the techniques on structures given explicitly. Our structure on which we dualize is given implicitly by irreducible elements. And that makes the difference. Yeah, that's the main point. And just 1 minute for saying about another setting. Actually, we can define a closure system by implications. It's like, it's well known in relational database theory. You define a closure of sets of attributes by applying functional dependencies until the saturation. If you have a closed set of attributes, closed now obtained by, this closure obtained by iterating implications, closed sets of attributes make a lattice again. But again, if you dualize on a lattice given implicitly by implications, functional dependencies, if you know it better, then again, dualization over it is not tractable. Again, because you can have exponential blow-up. Yeah, and then we come to the conclusions that we can enumerate all hypotheses in output polynomial time. It is impossible to enumerate minimal in output unless p equals in p. And that we showed that the problem of dualizing a monotone Boolean function on a lattice, when it is given by its irreducible elements, cannot be solved in polynomial time unless p equals in p. Same result when it is given implicitly by implications. But when the lattice is Boolean, then your irreducible sets is just atoms and coatoms of the Boolean lattice, and you can easily dualize over it using the algorithm of Fredman and Hachiyan. And the recent result by Mikhail Babin that you can extend this technique to distributive lattices, but the result is not very optimistic yet. It's sub-exponential. And it's, of course, not practical, because, I mean, you cannot guarantee that your data make a distributive lattice. It's just...
on general lattices, what is the upper bound?
It's exponent. It's just
linear.
Yeah, it's linear. And that's it. Thank you for your attention.
Questions? Are there some connections with the data structure called binary decision diagrams? because they also represent some exponentially large fractions with, but they represent it with diagrams.
Binary decision diagrams. It's, Yevtushenko dealt with it. You mean you want to represent data by binary decision diagrams, huh? Or what? It's like decision trees, but they can converge, the branches, yeah? Yeah.
I just feel that probably there are some connections with these branches. Okay,
And-
last question. And are some other classes of these lattices that have small contexts?
Sorry, last.
Here, by distributive lattices, you somehow characterized a lattice that has a small context, yes?
No, it's not necessarily this. Yeah, I mean, yeah, there can be big compression in distributive case, but it's not always like that. Distributive lattices are interesting with respect to the implication basis, for example. Implication bases have singleton premises. And that corresponds actually to the Birkhoff's theorem on distributive lattices, that they can be described as ideals of partial orders. There's an interesting on BDD. Sergey, do you remember there was a colleague from Kiev who 10 years ago he was interested in this relationship. Do you remember his results? Let's discuss it in more detail. Thank you.